Hello student, how are you? Today I am here with the new topic of second chapter, electrostatic potential and capacitance. The name of this topic is line integral. Line integral means that we can say that in case of non-uniform electric field, when we talk about non-uniform electric field and we want to carry unit test positive charge from one point to another point or between 2 points inside the electric field, then we use the term line integral. Here in definition you can see the line integral of an electric field between 2 points. Between 2 points is the amount of work done to carry, or you can say amount of work done in moving unit test positive charge between these two points. Means that electric field will do the work to carry this charge from point A to B. Then after that, if you want to carry this charge from B to A, then you will do the work against the electric field. Then the value of work done will be negative as the previous value. So here we will see that how we will solve or how we will calculate the value of electric field. So here you can see that this integral, this type of integral with L symbol, or you can say C symbol, this integral is called line integral in open loop. Line integral here, same, it is also known as line integral, but it is in open loop, or you can say that open line integral. When I talk about this type of symbol, it is used for closed curve line integral. Clear? Closed loop, the line integral is like this. For open loop, the line integral is this or this. So after that, I will write a small derivation for that. What is the meaning? What is the value of electric line integral? Means that what is the value of amount of work done to carry unit test positive charge in non-uniform electric field. See, from the given these type of lines, these are the lines which form non-uniform electric field. So under these lines I have taken 2 points A and B, and I want to move this unit test positive charge, which is test from here, which is at here, from point A to B with the help of electric field. So then we will take this charge from A to B, or we have different type of path to do work, because you know that electric field is conservative in nature. It means that the amount of work done to carry charge from one point to another point is independent from their path. You can carry the charge from A to B like this, and on straight loop. Clear? That's why it is conservative in nature. So here, if I want to carry this charge from A to B, then if you will take here any point and you will draw a tangent at this point. Suppose I consider this point is A. Suppose in here. So you will see that the distance AB makes theta angle with the electric field. First of all, you will do here small amount of work done, means that you will divide here the line segment AB in small type of elementary distance. Means suppose A and B is distances, AB distance is like that. So you will divide the distance AB in small type of line element. Point is clear? Of length DL or DL1, DL2, DL3, DL4 and so on. So that you will do the work for this elementary distance at each separation, and after that combine the whole work, and you will get finally the total amount of work done to carry this charge from A to B, or you carry the charge between 2 points, either A to B or B to A. So this work is EDL, and this is called as line integral. Calculate the line integral. Line integral means that amount of work done to carry unit test positive charge between 2 points by the electric field. To carry the line integral if dW is the amount of work done for elementary distance dl, elementary distance dl, then amount of work done, amount of work done. Listen student, here we are doing the work, means here we are calculating the work for unit test positive charge. So it is understood that the value of q naught is equals to 1 coulomb. When the value of q naught is equals to 1 coulomb, then you can see that the value of force with the help of this formula is equals to F is equals to E, because q naught or q value is equals to 1 coulomb, so the force is equals to numerically in electric field. So here total amount of work done for that case is E into dl, dot product of E and dl vector, and you have, it is very clear in front of you, the direction of dl vector means it is the direction of AB makes theta angle with the electric field. So I have written this displacement, elementary displacement here. You can use the word displacement in place of distance, displacement, elementary displacement. So for this elementary displacement, I will use here this dot product of vector. So see, EDL means EDL cos theta. So this is the amount of work done, or you can write this work like that again. Here E dW is equals to E dot dl. So this is the elementary amount of work done to carry the charge from point A to an elementary displacement dl. Therefore, total amount of work done, total amount of work done for carrying the charge A to B is integral of, this one is a line integral because this line is open, or you can say, if suppose I have drawn in place of line like a curve, this curve is also open, so I will use here open line integral L, or you can use C symbol here also. So it will be dw, and you will see here it is E dot dl. So this is your amount of work done by electric field to carry the charge from point A to B, or you can say between 2 points. So this is the amount of work done by electric field to carry the charge from A to B. If you want to carry the charge from B to A, then you will do the work against this electric field. So for that, if you can say here, in short, amount of work done, since you know that this is the amount of work done for A to B, now amount of work done to carry the charge from B to A. When you will do the work against B to A, means that when you will do the work against electric field, that time you can see here the work done will be B to A. It is opposite, means here AB is a displacement if I consider here, because I divide this distance AB in small type of elementary displacement. So here the direction is AB initially. Now we are carrying the charge from B to A. It is just opposite to AB, means like this in this direction. That time the angle between them is 180 minus theta. So we can say that cos 180 minus theta minus cos theta. So that's why we can use here see student, EDL is our work. You will see the work is negative when we carry the charge opposite to the direction of work done by electric. So this is in place of L, I have written A to B here. So here you can also use A to B. C and L is our general term. Here also you can use A to B. So see, again I am here. So see, here we are carrying the charge from B to A, and you have you can see here easily the angle between this electric field and the direction of B to A means BA displacement makes 180 minus theta angle with this. So I will use here B to A E dl cos 180 minus theta. So student, see here B to A E dl cos 180 minus theta is our minus cos theta. So this minus sign comes here. After using this, I will eliminate this from here. So after this negative sign, I will write this like that. So EDL cos theta will make again in dot product form E dot dl. So with negative sign. So we can say that if we carry the charge from point B to A, it means that against the work done by electric field, then the work done will be negative. As you know that electrostatic field is conservative in nature. It means that amount of work done doesn't depend on the path between these 2 points. So therefore we can say that it is conservative in nature, electrostatic field. And after that I have some important point for you. Now here I'm giving you some important point about this. So after the discussion of line integral, as you know that in discussion previous I told you electrostatic field is conservative in nature. How it is? It means that the work done doesn't depend on the path in which we are carrying the charge from one point to another point. So see here student, some important point. First point is that in electrostatic closed line integral of electric field, which is noted by like this, EDX is equals to 0. Remember these points. So if the closed line integral of electric field is 0, it means that amount of work done in this case is 0. So if the amount of work done for closed loop means that like this, when you are carrying the charge from one point to another point, so then you can see that the total amount of work done for closed line integral is 0. So you can say that electrostatic, it means electrostatic field is conservative in nature. Clear? Here, after this, we will talk about the second case for varying electric field. In case of varying electric field, the closed line integral of electric field means EDX is equals to, you can say that negative, this one is partial differentiation, so this one is change in magnetic flux B dot ds. So it can be written as d upon dt means d phi b upon dt. So here this is the equation, which is a part of electrodynamics, in which the electric field is varying. So here this equation is called, you can say this equation, Maxwell third equation. So these are the two equations. First is that in electrostatics, the closed line integral of EDX is equals to 0. It means that electrostatic field is conservative in nature. And the second one is that for varying electric field in which the closed surface integral, in which the closed line integral of electric field is equals to negative rate of change in magnetic flux, which is noted by this. After this, the new topic is equipotential surface. So student, we will see what is the meaning of equipotential surface and how we will. Now student, in this topic, equipotential surface, first of all we will read the definition of equipotential surface. As you know that by name, here we are talking about equipotential. It means that equipotential surface, it means that a surface in which at every point the electric potential is same. So on the same way I will explain the definition as I have written here. So see here student, equipotential surface is that surface at every point of which electric potential is same. Now see, as it is given here, since electric potential in electric potential surface EPS is represent as electric potential surface, we remain constant, means that definition said definition says electric potential is same at every place. It means that electric potential is constant. When the electric potential is constant, so it implies that electric potential difference is zero. When the electric potential difference is zero in equipotential surface, by using the definition of electric potential difference, we can say that W upon Q is called electric potential difference, and in equipotential surface equipotential surfaces delta V is equals to 0. So from this equation first we will get here Q into delta V, so Q into 0. So it means that amount of work done is 0. We know that the electric potential difference in equipotential surface is 0 from the above discussion. So we can say that the work done will be 0. It means that there is no work done to carry a charge from one point to another point in equipotential surface. For any elementary displacement dl over the equipotential surface, this is important point, see here student, equipotential surface. Clear? For any elementary displacement dl over the equipotential surface, we can see that amount of work done to carry unit positive charge. It means that here you will substitute Q naught is equals to plus 1 coulomb again. So see how much amount of work you will do in this equipotential surface in value. It will be, suppose dW, it is equals to E dot dl, and you know that since here we are talking about equipotential surface, it means that dW will be 0. There is no amount of work inside the equipotential surface, so dW is equals to 0. So we can say that E dot dl is equals to 0. This relation provides us a second important point, which implies that therefore we can say that vector E means electric field, comma dl means the elementary displacement over the equipotential surface are mutually perpendicular to each other. On the other hand, we can say that because we know that dl is the displacement over the surface, over the equipotential surface, so we can say that, electric field lines are perpendicular to the equipotential surfaces. Why? Because dl is over the equipotential surface. As we know that E is perpendicular to dl, so in place of E we can say that electric field lines, and in place of dl we can say that equipotential surface. So conclusion is that for any charge configuration at any point, the electric field at that point is perpendicular to the equipotential surface. Clear student? Means that here if I give you a charge plus Q, for this charge, for any charge configuration, we can say that the electric field, this is the direction of electric field outside the charge. This electric field is normal to the equipotential surface for any charge configuration. This point is clear or not, student? See here, what I want to explain in front of you, I am saying that here, if I am taking any charge configuration, see here, if any charge configuration, the electric potential, the electric, not equipotential, the equipotential surfaces at a point is perpendicular to the electric field at that point. Point is clear or not? So you can say that for any charge configuration, the equipotential surface, you can use this statement here also. Means that you will see that dl, we know that dl is over the surface, over the equipotential surface. I am taking one example here like this. This is suppose our equipotential surface. This is our surface, and I have drawn a line segment over them like this. This is your line segment. So if I draw this line segment over that surface, so if suppose after the calculation I got E dot dl is equals to 0, it means that the electric field will be normal to that dl distance. Means that because this line segment is over the surface, because this line segment is over that surface, so this surface is our equipotential surface. So here we see that for any charge configuration, suppose here any charge q is present, for any charge configuration we can say that the equipotential surface, this is normal to the electric field lines. Clear? Is normal to the electric field. Okay. So as we know that, since here one important point here, for a point charge, electric potential V is equals to 1 over 4 pi epsilon naught q over r. If the surface is equipotential, in equipotential surface, but we have equipotential surfaces, we know that V is equals to constant. If our electric potential is constant, because our electric potential is constant in equipotential surface, so from this relation supposed to be 1, we can say that if V is equals to constant, as we know that V is equals to constant, see here again, V is equals to constant, it implies that 1 over 4 pi epsilon naught already constant, charge is already constant, so we can say that R is equal to constant, means radius equals to constant. So the conclusion is that for a single charge, the equipotential surfaces are concentric circles. Equipotential surfaces are concentric circle such that charge is at their center. As you know that all concentric circles have same center. So if we talk about the charge, single charge, so the formation of equipotential surface is like a concentric circle. See the diagram here. If I talk about this charge Q, so the equipotential surface around this charge is in the form of concentric circle. As we know that V is equals to constant with this formula, with this formula we know that V is equals to constant in equipotential surface. From this formula we get R is equals to constant. So after this R is equal to constant, we can we can give a statement for that. If the value of radius is constant, it means that for a single charge the equipotential surface is in form of concentric circle. So see here, these are our concentric circles around a charge, around a single charge. So you can use dotted symbol here. So these are the diagram of equipotential surface around a charge, or equipotential surface for a single charge. So here if I draw the electric field lines, so you will see that the direction of electric field lines are normally perpendicular to that equipotential surface, because E dot dl is equals to 0. That's why. Students, point is clear, student? This is the direction of E, and this one is our concentric circles are our equipotential surface. So we can say that for any spherical object like this, in which the electric field lines are normally in outward direction in their surfaces. So this is the diagram for the equipotential surface. This is the diagram of equipotential surface line, equipotential surface for a given single charge. If we talk about the equipotential surface for uniform electric field, so you will see that if the direction of electric field lines are parallel to x-axis, then from the statement as we discussed, equipotential surface is perpendicular to the electric field. So this one is the direction of electric field, and from the previous statements we know that equipotential surface is normal to the electric field. So we know that the normal of this x-axis is a plane which is called which plane? YZ plane. So here we can see that the surface which is normal to the given electric field is parallel to YZ plane. So that's why we can say that for uniform electric field region, for uniform electric field region, the equipotential surface is parallel to YZ plane to the given electric field E along x-axis. Clear, student? So these are the diagrams of equipotential surface for a single charge, equipotential surface for uniform electric field region. Now after that I will draw a diagram for third case for an electric dipole. For an electric dipole. In case of electric dipole, you will see that. So students, see here I have drawn these two diagrams for first diagram for the electric dipole. This is the equipotential surface diagram for an electric dipole, in which you will see here this is the plus charge and this one is minus charge. So plus 2 minus the dotted lines around the charges positive or negative represent here equipotential surfaces in form of concentric circle. As we discussed earlier, V is constant, it implies R is constant. Individually these are single charges, so it is just like a concentric circle similarly here and here. And when we talk about whole dipole in which two equal opposite charges are separated each other at small distance, then you will see here these two charges, due to these two charges here the equipotential surfaces are very close to each other, means these surfaces lines are close to each other. It means that here the electric field region is stronger. Where the electric field region is stronger, in that place the electric field lines means equipotential surfaces are very close to each other. And where the equipotential surfaces is weak means that where the electric field is weak, in that places the equipotential surfaces are spaced apart. Clear? On the other hand, same way you will see here when we talk about the identical charges, these two charges are positive charges, and you will see here the electric field lines are represented by dark lines which is in outside direction. You can say that it is perpendicular to the given equipotential surfaces, and after that you will see when you will draw the equipotential surfaces for these two, then you will get this type of structure for equipotential surfaces. So here we discussed four types of equipotential surfaces. First of all, first diagram for a point charge means that uh, here we are taking single charge and we draw the equipotential surface around a single charge. Then after we talk about the equipotential surface for uniform electric field region. Then after third one is that about electric dipole, and fourth one is that two identical positive charges, two identical positive or two identical positive charges. Clear, student? And after that, after the whole discussion about the equipotential surface, I will here do the next derivation. Now here, for this derivation, in which we will find the relationship between electric field and potential, means electric potential. Here I have taken two equipotential surface, here A and B. These two are equipotential surface. Let us consider the equipotential surface. In equipotential surface A, the electric potential is denoted by V, and the electric potential at surface B is V plus dV along the direction of electric field, which is perpendicular to these two equipotential surfaces. Now here, to find the relationship between electric field and electric potential, we will do a work against this electric field. It means that the direction of electric field is from A to B. Here we will do the work to carry unit test positive charge from B to A, which is against the electric field, and then we will see that this work is stored as, because we are carrying unit test positive charge from B to A, so this work will be equal to the potential difference between these two equipotential surfaces separated at distance dr. Clear, student? So by this statement you know that VA and VB are the equipotential surface. So I will write here in short, amount of work done to carry unit test positive charge from B to A, which is against the electric field direction. So this amount of work done is dW. dW is equals to E dot dr, and we know that E dot dr means, here we are talking E dot dr, direction of E is along A to B, and we are taking or carrying the charge from B to A. B to A means from B to A, which is just opposite to electric field, so it makes angle 180 degree between them. So dr cos 180 degree. Since in this condition theta will be 180, and you know that cos 180 is equals to -1. So here EdR, it is equals to -1 dW. So your work done will be EdR with negative sign. This is the work done which you have done against the electric field. So by the definition of electric potential difference, we can say that when we carry the charge from B to A, means opposite to the direction of electric field, then we can say our potential difference is VB minus VA, which is equals to dW upon Q naught. Since here Q naught is equals to 1 coulomb of charge, so the potential difference VB minus VA is equals to our dW over 1. Clear? So you will get the value here, VB is equals to V plus dV from the given diagram minus V. After cancellation these, you will get the value dV is equals to dW, and you know that the value of dW is minus E dot dr, so I will write here minus E dot dr. So from this we will get here E is equals to minus dV over dr. Here the negative symbol, here the negative sign shows direction of E, direction of electric field E is along the decreasing potential, along the decreasing potential. Clear? Now after this I will write here the next definition, which is important for you, is potential gradient. So which is potential gradient means magnitude of this. It is the magnitude of change in electric potential in per unit displacement perpendicular, or you can say normal, to the equipotential surface at the point. So potential gradient at any point, we can say that here potential gradient at any point is the change in electric potential in per unit displacement, clear, normal to the equipotential surface. So dear student, potential gradient is magnitude of dV over dr, or you can write it dV over dr. These were the three topics which I have discussed in front of you: line integral, after that equipotential surface, after that the relationship between electric field and electric potential. All three topics are very important for your examination. So please students, revise this topic at your home. Thank you. Have a nice day, and thanks for watching this video. Thank you.